Well, we just saw how we can calculate mass percent composition from a chemical formula. We can also do the opposite. You can calculate the chemical formula from the mass percent composition. Now, if you already knew the formula, you probably wouldn't want to do this. But think about, we have this mystery compound. How do we figure out what the formula is? We don't know what it is. In modern times, there are many different ways we can do that. But one of the earliest, simplest ways it was done is they would take the compound, they would weigh it, and then they would break it down into its elements. And they would weigh each of the elements. You take the mass of the element divided by the mass of the compound you start with times 100, and you get the percent composition. The percent composition was originally found experimentally by taking something apart. When we use the percent composition to find the formula, this is the empirical formula. Remember, empirical means derived from or guided by experience or experiment. So the empirical formula comes from experimental data. It's going to give us the smallest whole number ratio of each type of atom that's in the compound. It's not going to tell us how many atoms of oxygen are in one molecule. It's just going to give us ratios. The molecular formula tells us how many atoms of each element are in one molecule. The molecular formula is probably more useful than the empirical formula, but the empirical formula is what we get from experimental data. The molecular formula is always going to be some whole number multiple of the empirical formula. So let's look at an example, hydrogen peroxide. So the actual formula for hydrogen peroxide is H2O2. One molecule, I should probably do colors, has 2 oxygen atoms and 2 hydrogen atoms. But an empirical formula that you would get from experimental data would give you the simplest ratio. The actual ratio is 2 to 2. What's the simplest ratio? 1 to 1. So that's the molecular formula. The empirical formula is HO. That's the empirical. Sometimes they're the same. An empirical formula can be a molecular formula. We look at H2O. That's the molecular formula for water. Can we simplify that ratio? 2 to 1? No, we can't. For water, the molecular formula and the empirical formula are the same. The molecular formula is still a whole number multiple of the empirical formula, but the whole number is 1. For HO, here's the empirical formula, here's the molecular formula. The molecular formula is the empirical formula times 2. Any questions? Here's an example. You can actually use a 9-volt battery to decompose water into its elements. So here we have leads coming from the battery into a beaker, and we have 2 test tubes here to collect the hydrogen and oxygen gases that are released. And here we see we have some oxygen gas forming here and some hydrogen gas forming there. There are twice as many hydrogen atoms as oxygen atoms, and so this volume is going to be twice as much as that. But when we weigh it, we find that we get 3 grams of hydrogen and 24 grams of oxygen. Even though there are more hydrogen atoms, they weigh a lot less. One oxygen atom is 16 atomic mass units. A hydrogen atom is 1 atomic mass unit. So it takes a lot of hydrogen atoms to equal the same mass. So if we do this experiment and measure the gases, we get 3 grams of hydrogen and 24 grams of oxygen. How are we going to figure out what the empirical formula is? Well, we can't get it directly from the masses because the formula relates numbers of atoms, right? So what we need to do is we need to take this this mass of hydrogen and figure out how many hydrogen atoms is that, or how many moles of atoms is that. And we need to do the same thing with oxygen. I'm going to peek ahead. Yeah. So what we're going to do is we're going to take each of these masses and find the number of moles, and then we're going to look at the mole ratio, because that's what the compound formula gives us. So these are the steps. Some people like lists of instructions. Here's your list. You start with the masses of each element. You convert the masses to moles, using the molar mass as a conversion factor, just on the periodic table. You're going to divide all the moles, divide all the moles by the smallest number. And then we're going to look at the numbers we end up with. We need whole numbers, right? We can't have, oh, this formula is hydrogen 2.97, oxygen 5.36 or something, because you can't have parts of an atom. You can only have whole numbers. And so sometimes we need to multiply things to get whole numbers. If these instructions aren't making sense, that's okay. Hopefully it'll make sense when we actually do an example. When we do this part, trying to get the whole numbers, there's 2 different approaches. There's one approach, recognizing the decimal equivalent of fractions and multiplying accordingly by the denominator. If you know how to do that, you're good. The other way is to consult a table like this or just use trial and error. But if you have a fractional subscript that is 0.1, you're going to have to multiply by 10, because 0.1 is 1/10. 0.5 is 1/2. You have to multiply by 2 to get a whole number. In reality, the most practical way for most students is to try multiplying by 2. If you don't get a whole number, try 3. If that doesn't work, try 4. If that doesn't work, try 5. Usually you don't have to go that high. We don't try to torture you with these problems. Let's do this example. Decomposition of water produced 3.0 grams of hydrogen, 24 grams of oxygen. Find the empirical formula. So the first thing, we've got the masses. We need to find the moles of each of these elements. So here's 3.0 grams of hydrogen. So I want to find out how many moles of hydrogen is that. I'm going to multiply by moles of hydrogen. I'm going to divide by grams of hydrogen. And I get the number from the periodic table. Periodic table tells me that 1 mole of hydrogen weighs 1.008 grams. So I've got 3.0 divided by 1.008. And I'm going to end up with 2.97619, and it goes on. When you're calculating empirical formulas, you do not have to keep track of significant figures, but you do need to be careful. We are going to end up with whole numbers. But if you round things off, you're going to end up with the wrong whole numbers. So our starting number had 2 significant figures. That means I want to keep more than 2 significant figures here. I don't want to round this to 3 because that might mess things up. So I'm just going to keep some extra digits there. I would say minimum of 2, but if you want to write all of them down, that's fine. So that's moles of hydrogen. And we're going to do a similar thing for the oxygen. We're going to take the 24 grams of oxygen, multiplying by moles of oxygen, dividing by grams of oxygen, so the units work out. We look at the periodic table. 1 mole of oxygen weighs 16 grams. 24 divided by 16. And this is equal to 1.5, and there's no other digits after that, moles of oxygen. Okay? Now we want the mole ratio. So what we're going to do is we're going to pick the smallest number and divide both of them by the smallest. That way we're going to get numbers that are 1 or larger. We want to get rid of the fractions and the decimals and stuff. So 1.5 is smaller, so I'm going to divide both of them by 1.5 moles of oxygen. Well, 1.5 divided by 1.5 comes out to be exactly 1. There is 1 mole of oxygen for every 1 mole of oxygen. Well, of course there is. But this one is going to give us the ratio between moles of hydrogen and moles of oxygen. So we take 2.97619 divided by 1.5 equals, and my calculator is showing me 1.9841 blah, blah, blah. That's moles of hydrogen to moles of oxygen. Well, is that a whole number? No. But are the 3 grams and the 24 grams exact, or is there uncertainty in those? There's uncertainty in those. And so there will be some uncertainty in our ratios. My guideline is if it's within 0.1 of a whole number, you can round it. So if this was 1.90 even, I'd say you can round that up to 3. If this was 1.80, I'd say probably not. Don't round it. We'll have to do some multiplying. But this is close enough to round, and so we're going to round that to a whole number. We're going to say that's 2. This now is the subscript for hydrogen, and this is the subscript for oxygen. So I get H2O. This 2 is that 2 right there. And this 1 is that 1 that I don't want to write, but it's understood. So the formula is H2O. Any questions? My question is, why does it have to be so hot in this room? Let's do another one. This one's a little more complicated. A sample of a compound is decomposed in the laboratory and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula. The math in these problems is not challenging. It's multiplying and dividing. But these problems can get tedious, and the hardest part is just remembering what you were doing and what you needed to do next. Because you can get lost. You start calculating and you can go off and calculate something that's just really beautiful but doesn't help you answer the question. So we're starting with mass of each element, 165 grams of carbon, and we've got 27.8 grams of hydrogen and 220.2 grams of oxygen. I'm going to multiply by a conversion factor corresponding to the molar mass. So I have moles on top and grams on the bottom. I look on the periodic table. 1 mole of carbon is 12.01 grams. The grams cancel out. So I get 165 divided by 12.01. 13.7. That's my minimum number of significant figures. I'm going to carry along 2 extras. So that's my moles of carbon. For hydrogen, got 1 mole of hydrogen on the top, and I've got grams of hydrogen on the bottom, so the units cancel out. And for hydrogen, it's 1.008. 27.8 divided by 1.008. 27. We should also have 3 sig figs. There's my 3, and here's my 2 extras, moles of hydrogen. And oxygen, same thing, 1 mole of oxygen, 16 grams of oxygen. I'm just converting grams to moles. And this comes out to be 13. This should have 4 sig figs, 13.76, and 2 extras. Start with mass, convert to moles of each element. Next, we pick the smallest number of moles and divide all of them by the smallest. Which one's the smallest? The first one, 13.739. So I'm going to divide all of them, 13.739. So that one's going to be exactly 1. This one, divide by 13.739. So 27.579 divided by 13.739 equals, this is 2.007. Need a decimal point in there. And then this one divided by 13.739. And that one, I mean, you can kind of guess that that comes out close to 1. Are these close enough to whole numbers that we can round them to whole numbers? Yeah, they are. So we're going to call this 2. We're going to call this 1. So this is the subscript for carbon, for hydrogen, and for oxygen. So we're going to have CH2O. That's the empirical formula. Any questions? Just take some practice. Here's another one. Ibuprofen, an aspirin substitute, has the mass percent composition given here. Calculate the empirical formula. What do we have to start with? We need masses of elements. They're giving us percentages. What do we do? We make it easy on ourselves and we say, well, if I had 100 grams of ibuprofen, how many grams of carbon would I have? 75.69. So what you do is you just choose a sample size of 100, and then the percentages are equal to the grams. So essentially you can just take that percentage and switch that unit percent to grams. So for the carbon, I've got 70, I got to pick a marker first. 75.69, come on, grams of carbon. For the hydrogen, that would be 8.880 grams of hydrogen. And for the oxygen, it would be 15.51 grams of oxygen. And then we're going to use the molar masses to find the moles. I'm going to start at the bottom because I'm bored with this. So 15.51 divided by 16. This gives me 0.96. I'm looking for 4 sig figs. 9693, carry 2 extras, that's the oxygen. For the hydrogen, 1 mole of hydrogen, 1.008 grams of hydrogen, 8.8 divided by 1.008. This is 8.73. Carry 2 extra digits, so 2 moles of hydrogen. And for carbon, 1 mole of carbon, 12.01 grams of carbon. 75.69 divided by 12.01 equals 6.302. Throw 2 extra sig figs in there, 25. So I'm converting mass to moles, and then I identify the smallest one. It's the oxygen here at the bottom. So that one's going to come out to be exactly 1. .73, whoops, 02 divided by 0.969375. This comes out to be 9.006. And this one, you might be tempted to say, oh, well, this is going to end up to be 6. You got to actually do the math. 6.30225 divided by 0.969375 equals 6.50135. Can I round that up to 7? Is it within 0.1 of a whole number? No, it's smack dab in the middle between 6 and 7. It's 6.5. We need to multiply it by 2. If we take this number times 2, still my calculator, times 2, now I get 13.00, I guess it would round to 3. Is that close enough to a whole number? Sure it is. We're going to call that 13. If I want these ratios to stay the same, I have to do the same thing to the moles of each of them. If I multiply the carbon by 2, I have to multiply the other ones by 2 also. So I multiplied that one by 2. I'm going to multiply this one by 2. That's going to give me 9.012. Also close enough to round to a whole number. We're going to call that 9. And then I've got this one on the bottom times 2 is going to be 2. So I've got carbon with a subscript of 13. What? Thank you. I didn't do that on my calculator. That was not good. Thank you very much. I got the .012 part correct, though, didn't I? I was focused on that. Okay, 18.012. We're going to call that 18. That's better. So we've got carbon, 13 carbons, and we have 18 hydrogens, and we've got 2 oxygens. And there's our empirical formula. That ratio, 13 to 18 to 2, cannot be reduced to simpler whole numbers because 13 is not divisible by 2. If you get a number like this and multiplying by 2 doesn't work, try 3, try 4, try 5. Well, I wanted to finish this chapter. Let's just go ahead and do this one and call it a day. So a 1.56 gram sample of copper reacts with oxygen to form 1.95 grams of the metal oxide. What is the formula of the metal oxide? So in our compound, what are the two elements? Copper and oxygen. So what's the mass of copper? 1.56 grams of copper. Okay, that's pretty straightforward. Are there 1.95 grams of oxygen? No. They're trying to trick you. They're saying the whole sample with the copper and the oxygen together is 1.95 grams. What's the mass of the oxygen? It's the difference. So if we take 1.95 grams, that's the copper and the oxygen, and we subtract the mass of the copper, 1.56 grams, that's the copper. That's going to give us the mass of oxygen. So 1.95, I said 5 and I pushed 6, minus 1.56, so 0.39 grams, that's the mass of the oxygen. You have to read the questions carefully. This sort of a trick will probably show up on the exam. It's not because I'm trying to trick you. I'm telling you about it. I'm warning you ahead of time. But some of you will write down 1.95 grams for the mass of oxygen, and you'll get it wrong. 0.39 grams oxygen. So 1 mole of oxygen, 16 grams. 0.39 divided by 16. 0.024375. There weren't that many, so I just wrote down all the digits. And then copper, 1 mole of copper. How many grams? Look at the periodic table. 63.55. 1.56 divided by 63.55. 0.024546 moles of copper. It's okay that those are small numbers. The ratios, you pick the smallest one. They're really close to each other, but the oxygen one's a little smaller. So we divide this one by itself. That gives us 1. And we divide this one by the same thing, 24375. Okay, and that gives me 1.007, blah, blah, blah. Can be rounded to 1. So our formula is CuO. Any questions?